Hi, what are the static equilibrium? Static equilibrium means no rotational or linear action. So if it's at rest, it remains at rest. From what we have learned so far, what generates a linear acceleration? Rotational acceleration is caused by torque. So for both rotational and linear acceleration to be zero, we know net force should be zero, net torque should be zero. Both of these conditions should be met for static equilibrium. That's all about this chapter. From here, if you understand these conditions for static equilibrium, also you need to be able to apply these conditions to real situations. Center of gravity is very similar to center of mass, but is center of gravity is equal to center of mass? It depends. This is center of mass. So center of mass, for a given center of mass, sum of all forces act like a single net force acting on that center of mass, right? What about the gravitational? For example, let's find the gravitational torque. Gravitational torque is sum of gravitational torque of all mass elements, which is r cross f here. If this is the axis of rotation, r for this mass element, I cross fi, sum of all these for I, all masses around mass distribution, should be the net torque is equal to cross product net force. Then we can say center of mass is equal to center of gravity. But does this always hold? It only holds, let's calculate this again here. Fi is mig, right? And when G is constant throughout the mass distribution, we can take this mi to here only when gravitational field is uniform. For small object near the Earth's surface, for example, we can treat the center of mass is equal to center of gravity. And this equation holds. So in that case, gravitational force on mass elements act like a single force acting on a point called center of gravity, and center of gravity is equal to center of mass when gravitational acceleration is uniform throughout the mass distribution. There are two kinds of stability. The static equilibrium. Stable equilibrium and unstable equilibrium. For example, compare these two. Both are at rest now. But if you give small perturbation, small force, then this object here will not fall down, and this object will fall down very easily. This is unstable equilibrium. This is stable equilibrium. What determines stable and unstable? The stability. For example, here in this curve, this ball is in stable equilibrium. If you give any disturbance, small perturbation, then the ball will return to the equilibrium. That's stable equilibrium. This is unstable equilibrium. If you give any little force, little perturbation, this ball will just move far away from the equilibrium position. There are other stuff, for example, neutral stable equilibrium. It's stable, but it's neutral. It doesn't go back, but it doesn't, don't worry about this. It's very confusing. But metastable equilibrium is stable, but only in local positions. If you give large perturbation enough, then it'll go away from the equilibrium position. So at large area, it's unstable, but only in small area, it's stable. This kind of equilibrium we call metastable. So for example, by looking at position versus potential energy curve, you can determine which position is stable equilibrium and unstable equilibrium. For example, here it's stable equilibrium because whatever object is at here, if you give force, because the force is minus du dx, restoring force works near the stable equilibrium. However, near the unstable equilibrium, the force is towards moving that object away from the equilibrium. What determines the stability? Second derivative of the potential energy curve. For that position to be equilibrium, net force on that object should be zero. So that means because net force is minus du dx, net force should be zero. So potential curve, the slope should be zero at the equilibrium position. And if the potential curve is like this, 아래로 볼록, second derivative is positive, then it's stable equilibrium. If the second derivative is negative, 위로 블록, then it's unstable equilibrium. And in 2D or 3D, there can be some very confusing point. For example, here, along this position, along this direction is stable, but along this direction it's unstable, right? This kind of position we call saddle point. Okay, so we learned condition for static equilibrium in this chapter, which is very simple. You've already learned all this stuff. Because net linear acceleration is caused by net force, and rotational acceleration is caused by net torque. For static equilibrium, rotational and linear acceleration should be 0, meaning requiring net force, net torque, both net torque and net force should be 0. And we also learned there are two kinds of equilibrium: stable equilibrium and unstable equilibrium. Thanks.